Good morning, everyone. Can you hear me? Okay. I'm a postdoc at Center for Applied Energy Research. Today, I'm going to make a presentation on catalytic conversion of carbon dioxide to formic acid high-value chemical. The amount of carbon dioxide in air is increasing day by day. So basically, anthropogenic that activities are responsible for it, like combustion of coal, natural gas, and the petroleum products are emitting carbon dioxide to air. So looking at the data of 2020, so we see the amount of carbon dioxide in air has already surpassed 410 ppm, which is about more than 500 times larger than uh, other greenhouse gases like methane and nitrous oxide. So we can say carbon dioxide gas is making a significant contribution for greenhouse effect. Uh, naturally and artificially, carbon dioxide is captured and it is converted to different products. It is a starting material for the synthesis of different types of chemicals like methanol, urea, carbon monoxide, methane, and so on. And we are targeting to produce formic acid. So now the question is, why formic acid? So looking at this plot gives free energy for different molecules. We can say this formic acid is very close to carbon dioxide. So it needs the lowest gives energy input for conversion of CO2 formic acid. Also that it can be converted to this using very cheap materials, easy water, and just what we need is suitable catalyst. So looking at the current market of formic acid, less than 1 megaton of formic acid is consumed because that it is very expensive. The production of formic acid involves a multi-step processes that we call chemical process. Here, if we are able to produce formic acid from carbon dioxide and water and using suitable catalyst, it will open two new areas for the application of formic acid, basically formic acid based fuel cells, and it will be a very good medium for liquid hydrogen storage. So this is how carbon dioxide gets converted to formic acid. The first step is the adsorption of carbon dioxide to the substrate with electrons. It is a linear molecule, fairly stable. This is a rate determining step, means the overall process depends on this. So if a CO2 molecule is weakly bonded to the substrate and with that protonation and interaction with the electrons, there is possibility of getting formic acid or formate ion if the pH is more than 3.75. If it is strongly bonded to the substrate, and there is possibility of getting carbon monoxide from which other C1 and C2 products can be obtained. However, the actual performance of the catalyst depends on the catalyst itself, pH, and also on the reduction potential. So this is our process for converting carbon dioxide to formic acid. So this is a reactor where pressurized carbon dioxide will be converted to formic acid, and the products will be purified and used for further purpose there. So here for this, we need first substrate, suitable substrates, so that we can load catalyst heavily, and we need different types of catalyst and that immobilizing the catalyst on the substrate and doing the catalytic evaluations. So we have used here commercial carbon cloth, and carbon aerosol was coated to carbon cloth by the polymerization of the resorcinol and formaldehyde, and we used very cheap metals, copper and tin, for making catalyst, nano copper oxide, tin oxide, and copper tin that nano composites were synthesized by using hydrothermal process, and the products were that immobilized by using the ionochromatography. So these pictures show the morphology of our electrode. This is commercially available carbon cloth. When it is coated with CX, it becomes highly porous. Compared to carbon cloth, this CX, carbon aerosol, is highly porous and it can hold very large amount of catalyst. We are getting catalyst loading and far larger than what is reported in the literature. So these three are catalyst coated electrodes. In this picture, we can clearly see the nanoparticles of the catalyst. Actually, these are copper discs, nano copper oxide discs. This is our lab scale that reactor. So this our electrochemical cell has two compartments. This is cathodic compartment. This is anodic compartment where there is counter electrode. This is our working electrode. That electrode coated with the catalyst and where CO2 reduction takes place. This is our reference electrode, silver chloride, and the carbon dioxide is purged into 1 molar potassium bicarbonate solution to get a pH of 7.6. And then this is here we have got a data logger for measuring that cell potential during the reduction process. Here this is the actual cathodic reaction. For carbon dioxide gets reduced to formic acid and water is oxidized to oxygen at anode, and this is overall reaction. For the evaluation of catalytic performance, and the working electrode was reduced, it was applied, negative potential was applied, and that the liquid samples were collected after a certain time. The performance was compared using this term, which is that Faraday efficiency. It is simply the percentage of a charge that is actually used to convert carbon dioxide to formic acid. So higher that Faraday efficiency means that a better performance. So here is the result from that copper oxide nanodisk. This is a Faraday efficiency for format ion, and is a function of reduction potential negative 1.3 to 1.4. This is corresponding current density. These are copper oxide nanodisk. So we are using this catalyst. We got a Faraday efficiency of 28% in 14 hours, and this is it produces formic acid in a very narrow potential range, about that negative 1.55. Literatures also reveal that this catalyst is very selective for carbon monoxide, but however, it does produce formic acid to some amount. So then we synthesize and tested tin oxide nanoparticles here. This figure shows that the morphology of the electrode, and this is a Faraday efficiency as a function of electrode potential. So here we got a peak Faraday efficiency at negative 1.45, which is 100 millivolt less than that copper one, and we got this Faraday efficiency of 58% in 14 hours. But there was this was using this Nafion, which is a cation exchange membrane that separates cathode and anode. We got some issues with that, and we replaced that with that this bipolar membrane FumaSafe, and with that we got 67% in 15 hours. That is very good. It is in the lab scale. So further, that we synthesize that copper tin oxide that nano composites. These are the pictures. When we introduce copper into tin, the part size of the nanoparticles is further reduced. We got that comparable to 100 nanometer particles using this copper tin, and these were used at different potential, and we got very good formic acid formation at even lower negative potential, that is 1.40, with close to 70% Faraday efficiency in 12 hours. So here I have given the compare the results over here. So while going from this copper to tin oxide composite, we see that the cell potential is very low. It means lower cell potential means we apply less energy, means we are getting more product, means it is energy efficient. Faraday efficiency is also good, and here reduction potential going from this negative 1.40 means we are getting formic acid at lower reduction potential. This is the reason for selecting that the bimetallic catalyst. This process is still going on. We are making catalyst and testing there in the lab scale, and ultimately they will be used for large scale applications. This is the summary from my talk. Copper oxide is selective for formic acid at negative 1.55, and with the tin oxide we got negative 1.45, and this bipolar membrane is more stable. And what we have, we are having some problem. There are some issues related to mass transfer in anode section as well as in the cathode sections. We are working on that part, and we will be pressurizing carbon dioxide gas and to get better performance of formic acid, and ultimately these results will be applied in the large scale. This is my research group. Thanks to DOE for funding this research and all of my teammates. Thank you.